Hi, my name is Lily Adlesick, and this is Lab 3 Black Hole for Physics 2211. Let's get started with a brief introduction. The purpose of this lab in part 1 is to calculate the mass of a black hole by analyzing the motion of a star orbiting the black hole. And in part 2, our purpose is to find the initial velocity needed of a spaceship to get close to the black hole. The key concepts and fundamental principles at play in this lab include Newton's second law of motion, also known as the momentum principle, Newton's universal law of gravitation, and differentiation and the product rule when it comes to the parallel and perpendicular components. And here you can see a preview of our results. Here are the important equations for part 1, including the gravitational force, net force, and then dividing net force into its parallel and perpendicular components. Part 2 uses our equation for gravitational force again while we are guessing values for initial velocity, and as you can see here, we have a new model. Here I have included some explanation and reasoning behind how we break up the parallel and perpendicular components of net force, as well as how we apply Newton's second law and Newton's law of universal gravitation. Now let's jump into our experiment. The system is a black hole and the surroundings are the star and everything else. Our procedure is to edit the starter code in GlowScript using the Python coding language to create a unique star trajectory keyed to my email address. In part 1, we estimate the mass of a black hole by analyzing a star's motion which orbits the black hole, and in part 2, we want to simulate the motion of a spaceship around a planet and the black hole by calculating all the necessary gravitational forces and using Newton's second law to predict the motion of the planet and the spaceship. Then we want to find the initial velocity for the spaceship to get close enough to the black hole without crashing and then leave the system. Our key assumptions are that the net force on the star is due solely to the black hole located at the origin, and the time between data points in the trajectory is 1 day. Now time for our computational model and GlowScript code. Here we have the initial conditions of our code. As you can see in the top corner, I set the seed to Lily Adlesick at gotech.edu, and some system properties. We have the gravitational constant g, which is 6.7 times 10 to the negative 11th. We have the mass of the star, which was given to us in the prompt of the lab. Delta t I set equal to 86,400. The time for the first observation data point is set to t equals 0, and then I added two variables. First, we have total mass. This is a placemat for the sums of all the masses to later use to compute the average mass of the black hole for our results by dividing this number by the number of repetitions through the loop. And I also added count to the starter code to be a placemat for a counter of how many repetitions we make through the loop. Here in the code, we are applying Newton's second law and iterating over our data values. We compute initial and final momentum vectors. We use our momentum equals mass times velocity equation. Then we calculate the star's change in velocity and change in momentum using equations we know. A good rule of thumb is that the change in something equals final versus initial. Then we calculate dp dt. Then we use Newton's second law to calculate the net force. And this is from our lab equations that we went over earlier. Then we calculate dp dt of the parallel component, and use Newton's second law to calculate the net force of the parallel component and set this equal to dp dt parallel. Then we do the same for the perpendicular component. Finally, as you see here, we apply Newton's law of universal gravitation to find the mass of the black hole. Here you can view the computational model in action and see how it gets its results. Finally, we move on to discussion and conclusions. Here are all of our results. For part 1, we have the magnitudes of net force parallel, net force perpendicular, as well as the mass of the black hole, and in part 2 we have the initial velocity of the spaceship. And here I have plotted the magnitude net force versus the magnitude of net force parallel and the magnitude of net force perpendicular so that the three can all be compared. The graph shown is time in seconds versus magnitude of force in newtons. Analysis part 1. What does it mean? Net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components because in part 1 of this lab we were solving for dp dt and we were concluding that it was equal to the net force. Therefore, we are really just deducting the value for the net force. Analysis part 2. What if instead of wanting to take a quick look at the black hole and leave, you decide you want to enter into an orbit around the black hole? What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? Using trial and error with the code and testing out different initial velocities, I found the orbit using time equals 120 minutes and initial velocity equals, in component form, negative 2.3 times 10 to the 5th, comma, 1.1 times 10 to the 7th, comma, 0 meters per second. And below you can see the lines of code I edited in GlowScript as well as the computational model. Thank you for listening to my physics lab, and I hope you have a nice day.